Hey, welcome to this next calculus production. Today we're going to be talking about one-sided limits. So we've already looked at this graphically, the concept that you can calculate a limit from only one side or the other, from either from the left or from the right. And we're going to talk about this concept algebraically. So how it applies algebraically if you're given a limit and you're not giving it graphically. Okay, so let's get started. It's a little bit easier than you might think. So let's talk about how to find one-sided limits algebraically. I want to find the limit of x squared as x approaches 3 from the left. So normally what we would try first is we would simply try direct substitution. If it were to say the limit as x approaches 3, let's say, but this says the limit as x approaches 3 from the left. Well, the good news is you can still use direct substitution. So if I take 3 and I substitute it in and square it, I get 9. That's it. The limit is x squared as x approaches 3 from the left is 9. Okay, so it can be that simple. All right, so let's try the one underneath. Again, another one very similar to what you've done before. The limit as x approaches 5 from the right of x squared minus 25 over x minus 5. Now, if I split this limit apart, because there's a numerator and a denominator, and I find the limit as x goes to 5 from the right of x squared minus 25, I get 0. And then the limit as x goes to 5 from the right of x minus 5 will also be 0. That's 0 over 0. We know that to be indeterminate. So we need to figure out what would an algebra 1 kid do, and an algebra 1 kid would factor this, right? So the limit as x goes to 5 from the right. The top factors is the difference of two squares, x minus 5 times x plus 5 over x minus 5. Those two cancel each other out. And the limit as x goes to 5 from the right of x plus 5. I substitute the 5 in, I get 5 plus 5, which is 10. And that's my answer. Okay, so in some cases, nothing's different. We've already known how to do this, and nothing's different at all. However, there are some different kinds of one-sided limits that we're going to look at here that might be a little bit different. So let's take a look at some piecewise functions and limits. Okay, so let's try to find the limit. Let's take our piecewise function f of x equals x plus 3 if x is less than 1, and x squared minus 7 is if x is greater than or equal to 1. Now remember, what this means is that 1, I call 1 the change point. Okay, so it's going to change at x equals 1. You're going to change from one function to the other. All right, and that change point, the fact that it's a piecewise function and it has a change point, is going to be important, not just for this lesson, but for a lot of them. So it's something that you should know, okay, and be familiar with. So let's calculate a couple things. Let's try to calculate f of 1. Well, f of 1 just means x is 1, and it's got to go into one of the two pieces. It can only go in one or the other. So I'm going to look at my restrictions. This one says x has to be less than 1 for it to go in there. The top piece, that's no good. The bottom piece, x has to be greater than or equal to 1. Well, that's good. So I'm going to take 1 and substitute it into the bottom piece, and I get negative 6. So f of 1 is negative 6. There's my answer. But now let's make it a little bit more interesting. Let's calculate the limit as x approaches 1 of f of x. Now the problem with finding the limit as x approaches 1 of f of x is that 1 is where the function changes from one piece to the other. Okay, so if you look at your little number line here, here's 1. On the left side of 1, if x is less than 1, you're on the piece x plus 3. But if you're on the right side, you're on x squared minus 7. So the issue is, how would you calculate the limit as x approaches 1? So what we would have to do is we're going to have to calculate the limit from both sides, because technically you're on two different paths depending on which side of 1 you're on. So we're going to have to break this up. We're going to have to calculate the limit as x approaches 1 from the left of f of x, and we're going to have to calculate the limit as x approaches 1 from the right of f of x. And what we're going to hope is that the two limits come out to be the same, right? Because that's what it means for a limit to exist. The two limits from the left and from the right have to go to the same place. So this is an algebraic look at something we've seen graphically. Okay, as x approaches 1 from the left, so we're just smaller than 1 coming in this direction, we're on this graph, x plus 3. So that means we're going to have to take 1 plus 3. That gives me 4. But as x approaches 1 from the right, so that means we're coming in this way, just bigger than 1. We're on the x squared minus 7 graph. So that's 1 squared minus 7. That's negative 6. So these two limits from the left and from the right, they're not the same. So the limit as x approaches 1 of f of x, this limit does not exist. Because from the left and from the right, I don't go to the same place. And that's one of the few scenarios where you can write down the limit does not exist. Okay? All right, now let's try this one underneath, which is a little bit, I guess, maybe weird. It says the limit of f of x as x approaches 5. Well, 5, well, this limit as x approaches 5, here's 5, okay? And the issue with 5 is, if you approach 5 from the right, this way, you're using this x squared minus 7 graph. But if you approach 5 from the left, remember, you're very, very, very close to 5, right? You're not anywhere near 1. 1 is the change point. 1 is where you already switched over from this top graph to the bottom graph. So if you're really, really, really close to 5, from the left, you're also on the graph x squared minus 7. So all I need to do here is take 5 squared and subtract 7. I'm only going to be on this bottom piece if x is at 5 or near 5. So that's 25 minus 7, that's 18. That's the limit. I don't need to calculate the limit from the left and from the right because I'm so far away from the change point that I know which graph I'm definitely going to be on. I'm going to be on that x squared minus 7 graph. Okay? All right. So that takes care of that. Now, if you wanted to look at this graphically, just so that you can see what the heck is going on here graphically, if I were to graph this, x plus 3, so y equals x plus 3 if x is less than 1. So let's see. We go 1, 2, 3 up. There'd be a point there, but I can't. Oh, yeah, I can draw that point there. Yep. And then I go up 1, 1 to the right. So there'd be an open circle there. And then my line would come down this way. And then x squared minus 7. That's a parabola, moves 7 spaces down. So let's say this is negative 7 here. And then I'm going to go up 1, 1 to the right. Get a closed circle there. And I'm going to have a parabola that looks like this. Okay. So parabola, it opens up. So you can see, as x goes to 1 from the left and from the right, I don't go to the same place. But as x goes to 5, well, 5's over here somewhere. I don't know. As x goes from the left and from the right, I'm on the parabola, no matter what. So I don't have to worry about splitting it up and doing it in separate limits. Okay? All right, let's try this one real quick. G of x is equal to the piecewise function x plus 1 if x is not 1, and 4 if x is 1. Okay, so let's calculate the limit, and then we will also, well, let's take a look at the graph first. I think that might be easier for you folks to see if we look at the graph. Okay, so this graph is the graph of y equals x plus 3 as long as x is not 1. So I go up 3, make a point, and then I got to go up 1, 1 to the right, or I could go down 1, 1 to the left. Now the only problem is at x equals 1. At x equals 1, the y value is 4, so there's a point on the graph called 1, 4. All right, so I'm going to put an open circle here. Okay, open circle. Or no, filled in circle here. There we go. And then I'm going to draw my line. So there's my line. So I actually make a full line. It's a complete line. Okay, this was supposed to be an open circle here at 4. This was a poor choice. Maybe I'll change it here real quick. So let me make this 0.15. So we're going to change this 4 to a 5. So that changes my graph slightly. There goes the whole graph. I'm going to put that open circle there. And 1, 5, there's a point there. There it is. So this is what my graph looks like now. That's a little better. That's a little more interesting this time. Okay, so I have this open circle at 1, 4 because it's not on the graph because x can't be 1, right, on y equals x plus 3. But there is a point at 1, 5. So let's do the bottom one first. I want to know what g of 1 is. So I'm looking for the closed circle. Where's the closed circle? On 5. So g of 1 is 5. But now I want to calculate the limit as x approaches 1 of g. Well, as x approaches 1 for g from the left and from the right. From the left, I'm on the curve x plus 3, right? I'm on this line from the left. And then from the right, I'm also on x plus 3. So if I do it separately, find the limit as x approaches 1 from the left of g, and the limit as x approaches 1 from the right of g. From the left, I'm on the line. So I'm going to take 1 and add 3. It gives me 4. From the right, I'm still on the line as I'm approaching 1. Remember, I'm not standing on 1. I'm just approaching it. So that's 1 plus 3. That's also 4. So the limit as x approaches 1 of g of x, we'll write it down here, is 4. And that's my answer. Okay, so this was a little different. That's the reason why I changed the 1, 4 point, because when I plug 1 in here, I happen to get 4, and I didn't want to fill in that circle. I wanted to make an open circle on the line and then make a filled-in circle somewhere else at x equals 1 so that you could see that they can be different. Okay? All right, so now let's go to piecewise functions and limits. So now this is absolute value functions and limits. All right, so let's take a look at something that has absolute value. Although, spoiler alert, piecewise functions are going to play a role in this. So let's find the limit as x goes to 0 of the absolute value of x over x. So now we could split this apart, right? We're going to get 0 on the top, and certainly we're going to get 0 on the bottom. So that's 0 over 0. That's indeterminate. The question is, what would an Algebra 1 kid do? Well, an Algebra 1 kid would probably be confused because they don't really know what to do with the absolute value of x. What they really want to do is just cancel the x and the x. You cannot do that. Do not do that. That is illegal. Okay? So what are we going to do with it? Well, an Algebra 1 kid might be confused, but an Algebra 2 kid might have a better idea. In Algebra 2, you learn that there's an algebraic definition for the absolute value. The absolute value of x is a piecewise function. Now, it's a piecewise function because the absolute value does 2 different things to a number. Okay, think about it. If I ask you to find for me the absolute value of 7, you get 7. If I say take the absolute value of 8, you get 8. If I tell you to take the absolute value of negative 2, you get 2. If I tell you to take the absolute value of negative 5, you get 5. So what does the absolute value do? It does 2 different things. If the number's positive inside the absolute value, it does nothing, right? The number that you put in is the same number you get out. But if the number inside is negative, what it does is it magically makes that value a positive, okay? So it makes that value a positive when it was a negative a moment ago. So the absolute value of x can be defined as a piecewise function. So let's take a look. Let's start with 2 scenarios. If the number that I plug in for x is greater than or equal to 0, okay? If that number I put in for x into the bars is greater than or equal to 0, the absolute value, down here, it does nothing, right? So the same number that I put in, which is x, that positive number, is the same number that I'm going to get out. So I get x. Okay? The number that I put in, which is 7, or whatever it is the same 7 that I got out. This number that got put in is the same number that got put out. So now, what happens if the number is negative? Well, if the number is negative, let's say I plug this number in. I'm calling it x. This is the number I put in, -2. I don't get the same number out. I don't get x out again. What I get is I get its opposite. Okay? So I put a negative number in for x, and the number that came out is the opposite of that negative number, which makes it a positive. I'll show you down here. If I put -2 in for x, I have to negate it to make it a positive, which is the answer I get out. Remember, x is -5. I put -5 into the bars. What comes out? The opposite of that number, which is 5. So the absolute value of x, if x is smaller than 0, is equal to -x. So now I want to calculate the limit as x goes to 0 of the absolute value of x over x. Well, since this function, absolute value of x, changes at x equals 0, it's got two different values depending on which side of 0 you're on, right? Here's 0. If you're coming in from the left, you're on the graph of -x. If you're coming in from the right, you're on the graph of +x. Then I have to do this in two pieces. I have to try from both sides. So what is the limit as x approaches 0 from the right of the absolute value of x over x? And what is the limit as x approaches 0 from the left of the absolute value of x over x? The limit as x approaches 0 of the absolute value of x over x, well, if you approach 0 from the right, I'm on the top piece. I'm on x divided by x. Well, x divided by x. Now the bars are gone. I can cancel these x's. I get 1. As x approaches 0 from the left, from this way, I'm on the graph of the bottom piece, -x. So that's -x over x. Now the bars are gone. I can cancel these x's. I get -1. From the right, I get 1. From the left, I get -1. So the limit as x goes to 0 of the absolute value of x over x does not exist. And that's the correct answer. That limit does not exist. Okay, so last one. Let's try to do a little bit of a variation. The limit as x approaches 2 of 3 times the absolute value of x minus 2 over x minus 2. So first things first, if I were to substitute 2 into the numerator, I'd get 0. And in the denominator, I'd also get 0. That's 0 over 0. That's indeterminate. So the question is, what would an Algebra 1 kid do? So an Algebra 1 kid hopefully would recognize, hey, that the absolute value of x minus 2 means something. It's a piecewise function. Now, we have to be a little bit careful. Remember, we're trying to figure out, right, when this thing is positive, when the bars don't do anything to it versus when the bars do something to it. So if you have x minus 2, well, if x is a number that's greater than or equal to 2, think about that. X is a number bigger than or equal to 2, and I substitute it into the bars, it's going to give me a number that's positive, right? 2 minus 2 is 0. 0, the absolute value of 0 is 0. So 3 minus 2 is 1. 4 minus 2 is 2. 5 minus 2 is 3. And then the absolute value doesn't do anything, right? We just talked about that on the last slide. So if x is greater than or equal to 2, the answer is just what's in the bars, x minus 2. But if x is smaller than 2, so now think about it. If x is 1, I get -1. If x is 0, I get -2. -1, I get -3. And again, all these are inside the absolute value. So I'm going to need the bars to negate the thing. So I'm going to have to negate what's inside those bars to make it a positive. So there's my definition for the absolute value of x minus 2. So now, again, 2 is where this graph changes from one piece to the other. So I'm going to have to split this limit up into 2 different pieces. I'm going to have to try the limit as x goes to 2 from the right. 3 times the absolute value of x minus 2. over x minus 2. And then the limit as x approaches 2 from the left, 3 absolute value x minus 2 over x minus 2. On the top, as x approaches 2 from the right, we would use the top piece, right? So it's a number bigger than 2. 2 from the right, we're at a number bigger than 2. That's the top piece. So the answer to that, the absolute value of x minus 2 is just x minus 2, no absolute value anymore. Over x minus 2, these cancel, and I get 3. The limit as x goes to 2 from the left means smaller than 2. That's this bottom piece here. So that's going to be 3. Oops, I forgot the limit sign both times. Okay, that's going to be 3 negative x minus 2 over x minus 2. So these x minus 2s are going to cancel, and I get negative 3. So that means the limit as x approaches 2 of 3 times the absolute value of x minus 2 over x minus 2. That limit does not exist. And that's the correct answer. Okay? And that's all there is to it. All right, and as always, thanks for clicking.